Greetings, Honors Chem students. This is my trusty assistant here. This is Thing from the Addams Family, if any of you have watched that recently. He's assisting me today and doing a great job of it, I might add. Today's lesson, we are looking at had we been in school, Friday the 20th of March, which would have been our last day of school prior to our regularly scheduled spring break. And so today we're going to talk about the fourth colligative property, freezing point depression. Yesterday's homework was over boiling point elevation. I did not collect that assignment. That's going to show up on the review that's forthcoming. And the calculations we're doing today in freezing point are very similar. So make sure you check your answers on that assignment with the answer key that I provided you in Canvas. And if you have any questions, again, shoot me an email, let me know. The assignment today, the freezing point depression assignment, I was going to collect, and so, or am going to collect. And so that would have not been due until we return to school from spring break. Of course, now that has all changed. But again, I'm keeping the do nows in their original state so that you know how things would have played out had we actually been in school. I think that's it. So let's get going here on freezing point. Scoot that down a little bit. All right, so again, because vapor pressure is lowered by an increase in solution concentration, the solution now stays in the liquid phase over a larger temperature range than what the pure solvent would have been. Again, I've explained this several times, but now we're going to look at this end of the extension. So water normally is a liquid above zero and less than 100, but when you add a solute to water and make a solution out of it, that temperature range that water remains a liquid is now extended in both directions. We talked about yesterday that the boiling point goes higher. Today, the freezing point goes lower. So let's take a look at an example, several actually, of how this can be utilized in the cold months to our advantage. First one is, again, I talked about putting antifreeze in your radiator so that your car doesn't boil over in the summer. Well, not only is it good for that, but it's especially good in the wintertime where it prevents your radiator's contents from freezing. So think about that. So if we just had pure water in your radiator in the cold winter months, water normally freezes at 0 Celsius or 32 Fahrenheit. So what that means is if you just have water in your radiator and the temperature at night drops, or in the day, drops below 32 Fahrenheit, then that water's going to freeze. Of course, you all know that water expands when it freezes, which means it's going to expand in your radiator, crack it, and then you're looking at about a $700 bill minimum to replace your radiator, which is not cool. So, no pun intended. So, we use a solute, in this case, antifreeze. I talked to you about the good properties of antifreeze as a solute. They still apply here. So if you've ever put antifreeze in your radiator and you've read the bottle, it says, well, if you put in so much antifreeze to so much water, whatever the ratio is that they give you on there, it'll protect your engine down to minus 30 Fahrenheit, for example. So that's taking into account this exact thing right here. So if you put antifreeze in your radiator and make a solution, then that drives the freezing point down. Okay, so let's say your engine's protected to minus 30. That means unless it gets to minus 30 degrees or lower on an extremely bitterly cold winter night, then that solution is not going to freeze. That is a good thing. I have another example of that up here on the board. This is why we throw rock salt on the pavement in the wintertime once we get a snowfall or ice. So let's talk about that. So let's say, for example, that the temperature outside on a winter day or night is 20 degrees Fahrenheit, which is minus 6.7 Celsius. Okay, that is below the normal freezing point of water, all right, which is 32 Fahrenheit or 0 Celsius. So if we get any precipitation at a temperature of 20 degrees, we're looking at ice and snow, probably mainly snow, and it is going to remain frozen, all right, because we're below its freezing point. So if we get some ice and snow, the freezing point of that ice and snow is 32 Fahrenheit or 0 Celsius. If we're below that temperature, which at 20 Fahrenheit we are, then that ice and snow remains frozen. However, we get out there and the highway department blades off as much of that snow and ice as they can, and then they drop some salt and or sand. Sometimes they use a combination of both, which is fine. They both will do the trick. I think they use the sand mainly, though, to increase the friction coefficient. It's makes for a rougher surface, which helps with the sliding of your tires on the pavement. And so, but what they do that for is to drive the freezing point of now the solution of ice, snow, and the rock salt and or sand down. I used an example here of a mixture based on calculations of 8.33 mol solution concentration. That would drop the freezing point of that ice and snow down to minus 15 Celsius or 5 degrees Fahrenheit. And if the temperature is still 20, then what that means is now the freezing point of this solution is lower than the air temperature. And so that means then that 20 degrees Fahrenheit would now be above the freezing point of this new solution, and thus the ice and snow melts. All right. So without changing the air temperature at all, we can adjust the freezing point of that ice and snow by adding a solute to it and making a solution, which will drive that freezing point temperature down. Net result, it melts. So again, a very good thing. So let's look then at, so this is called freezing point depression. Okay, boiling point elevation is because the boiling point elevates or raises when you add a solute to it. And as we have said, the freezing point does just the opposite. It lowers. And so we call that freezing point depression. So pure water, again, normally freezes at 0 Celsius or 32 Fahrenheit. The addition of 1 mole of any non-electrolyte solid particles to 1 kilogram of water, again, this is a 1 mole solution, will lower the freezing point by 1.86 degrees Celsius, almost 2 degrees. This is called the mole freezing point constant, or Kf, of water. And again, as I refer back to the handout that we looked at yesterday, the lower portion of that handout lists some freezing point constants for various solvents. Again, I have water listed first because it's by far the most common solvent we use, but I listed a few others beneath it. So these are now freezing point constants, or Kf. Now, as far as the calculations, this equation should look pretty familiar to you because it essentially is the same exact equation that we looked at yesterday. Only now, instead of the change in the boiling point temp, it is the change in the freezing point temp. Instead of the boiling constant Kb, it is now the freezing constant Kf. And then this still is the molality of the solution because, again, colligative properties mathematically rely on molality. Okay? So if water is the solvent, then once you calculate the change in the freezing point, you now subtract that number from its original freezing point. Remember, freezing point depresses or goes down as compared to boiling point going up. So the new freezing point temp is equal to the original freezing point temp minus now the change in the freezing point. All right, minus. So that's the difference. Again, if water is your solvent, then the original freezing temperature is 0 Celsius. If it is some other solvent, again, I would have to give you that solvent's original freezing point. And I believe there is at least one problem, if not two, on your homework where water is not the solvent. So you need to make sure, number one, you use the correct freezing constant, and number two, make sure you use the correct original freezing point. In addition to that, in determining molality, remember the kilograms of the solvent. If that solvent is not water, then you're probably going to need its density to get from a volume to kilograms by using its density equation first. If it gives you the solvent in grams, then you could do the conversion to kilograms directly. But if it gives it to you in volume, you would have to use its density to get from volume to mass first and then to kilograms. So make sure you're aware of that. All right, so let's look at this first example. These two examples today are very, very similar to the ones we did yesterday. The math is almost the same, okay? But again, here's where it differs right here. So this first one asks, what is the freezing point of a solution? So we're looking for the new freezing point temp then that has been made by dissolving 125 grams of glucose. So there's the mass of our solute in 725 mLs of water. So water's the solvent. That has to be in kilograms for molality. So again, since it's water, we can make that conversion directly, since an ml and a gram are the same. So move the decimal 3 to the left or divide by 1,000, 0.725 kilograms there. So we need to know the molality first. So just like yesterday, we're going to find the number of moles of our solute before we can determine its molality. So the mass is 125, and then our solute is glucose, which again is 72, 12, and 96, which is 180 grams per mole. So 125 over 180. This will not be rounded because it's an intermediate calculation. 0.69, and then 7 fours. 3, 4, 5, 6, 7. That's how many decimal places my calculator goes out. So there's the number of moles there, unrounded. The molality of the solution then is moles over kilograms. So the moles of our solute was 0.69444444 over the kilograms of water, 0.725. And again, on your assignment, just as in yesterday's assignment, I asked you to calculate a molality as part of the calculations. So since it was asked for, that would need to be rounded. And so I'm going to round that here just to keep it consistent. So that comes out to be 0.958 molal. 0.958 molal. Now, we can get the change in the freezing point temp is equal to Kf, the freezing constant, times the molality. Kf for water, 1.86. The molality, 0.958. And so the change in the freezing point to 3 sig figs based on our data, 1.78 degrees Celsius. So that is the change in the freezing point. So to calculate the new freezing point, here, the new freezing temp would be water's original freezing point, which is 0, minus now the change. And again, with water's freezing point being a constant, we will keep the 2 decimal places, negative 1.78 degrees Celsius would be the new freezing temperature. Okay. Here's another great application of freezing point depression. How about making ice cream, which I completely plan on doing, assuming we return to school. That is actually lab 10-2, I believe. Any of you ever made ice cream at home? Excuse me, I'm getting a little cotton mouth here. If any of you have ever made homemade ice cream at home, you know, you make the mixture in a container and then you pack that container in ice. But if you just pack it in regular ice, all right, so that ice freezes at 0 Celsius, 32 Fahrenheit, it is not going to get your ice cream cold enough to freeze. All right? Ice cream freezes at around -2, -3 Celsius. So pure ices won't do it. So we add ice cream salt. You can buy it in the store, or rock salt or some such thing. And you add that to the ice that surrounds your ice cream mixture, and that then creates a solution which drives the temperature down. All right. Since it drives the temperature down lower than the freezing point of ice cream, your ice cream freezes. So we'll put that to the test when we get back. So anyway, let's go on to the next one. You up for some homemade ice cream, Mr. Choff?
Possibly.
Possibly.
Lactose intolerant.
Oh no. You know what? I've had some students that were, and they brought in some of that lactate, and we made it with that. It came out just fine.
Okay.
So there you go. We've taken care of that. That's already been tested. All right. So for those of you out there that are lactose intolerant, keep that in mind. I would need to have you bring some lactate the day before lab, and we can still make your ice cream. All right. So the next example, again, is a little bit different. We're actually going to work backwards, so to speak. So here we are given the freezing point of a solution that was made by adding methanol to water is -3.88 degrees Celsius. Okay, so that is the new freezing point solution. All right. So water normally freezes at 0. So the change in the freezing point temp then is 0 minus -3.88, or a change of 3.88 degrees Celsius. So that is the change in the freezing point, 3.88. Now, how do we get the molality? Well, like yesterday, if we know the change in the freezing temp and we know the freezing constant, then we can use that equation to determine the molality of the solution. So if we plug in 3.88 here, the Kf for water is 1.86 times the molality. So we'll divide out the 1.86, and that gives us a molality of 3 sig figs, 2.09 mol. 2.09. Then in part B, it asks what mass of methanol, so now we want to know what mass of our solute did we dissolve in this solution if we use 925 mLs of water. So the water being the solvent needs to be in kilograms, 0.925. Again, I would caution you on your homework to make sure that if your solvent is not water, that you convert to kilograms appropriately. All right. So we have our molality, we have our kilograms. So we use the molality equation to get then how many moles of methanol are in this solution. So our molality was 2.09 equals N over 0.925. Put that over 1 and cross multiply. So N then would be 2.09 times 0.925, which would then, unrounded, give us 1.93325 moles. We can then find the mass of our methanol, our solid, by using the relationship between mass moles and molar mass. Our little shortcut there, N equals M over MM. So the moles is 1.93325 equals M over. So we need the molar mass of methanol, which is CH3OH. Again, hopefully you remember that from organic. So we got 12, 3, 16, and 1, which is 32 grams per mole for methanol. So 32 there. Again, we can place that over 1 and cross multiply. So M then is 1.93325 times 32. And to 3 sig figs, 61.9 grams of methanol. So if we take 61.9 grams of methanol, dissolve it in 0.925 kilograms of water, we will get a solution that has a molality of 2.09 molal and will then result in a new freezing point of minus 3.88 degrees Celsius. So that concludes today's lesson. And again, check please do it at home. Check your answer key that's posted on Canvas. If you have any questions, let me know. And until next lesson, I will say goodbye and take care of yourselves. And I hope to see you all sooner than later. So anyway, till next time, see you later.